Okay, in this video we're going to look at a few more examples of applying the kinematics equations for constant acceleration. Okay, in this example we have an airplane which is initially at rest and it accelerates down a runway at a rate of 3.40 meters per second squared for 29.4 seconds, at which point it lifts off the ground. Question is, determine the distance traveled before takeoff. So you can see that I have again drawn my coordinate system here and this beautiful rendition of an airplane. I always advocate that my students draw pictures whenever they work a physics problem. I myself am not a great artist. No one would ever accuse me of that. However, I can draw boxes and triangles and circles and things like that. That's really all you need, but some physical representation with that coordinate system. Now I'm going to list what I know. I know the initial position is 0. Why do I know that? Because I can put my coordinate system where the thing launches from. So I can set it to be whatever I want. So it takes off from rest. I put my coordinate system right there. Now I know it's going to travel some delta x, and that's what I'm looking for, but we're also given that there's an acceleration and a time. The initial velocity is 0, the initial position is 0. And we have these three equations, our kinematics equations for constant acceleration. So we're looking for an x, and so we might use this equation, we might use that equation. Obviously, we're not going to be able to use that first equation because it doesn't have an x in it. Now, looking at this equation, I don't know what the velocity it has when it lifts off. I don't know that final velocity. And so I don't know delta x, I don't know VF. There's two things in this equation that I don't know. So in theory, I could use this equation to find VF and then plug it into there. But let's look at this middle equation. X is equal to x naught, I know that. V naught t, I know V naught is 0 because it starts from rest. I know the acceleration, I know the time. This equation will give me everything that I need. So that's going to be the fastest route to solving the problem. So just to be aware, I know that that term is going to go to 0. I know that V naught is 0 because it starts from rest, and so this whole term will cancel out. Anything multiplied by 0 is 0. And I'm left with my x value is equal to 1/2 at squared, and my a is given here at 3.4 meters per second squared. My t is given here at 29.4 seconds, so it's just at this point going to be a matter of plugging and chugging. So I have my kinematics equation here. This is the second kinematics equation, which I've eliminated all the terms that go to 0. I plugged in my a here, I plugged in my t there. Be sure that you square it. And what I find is that the distance traveled, or the final x position, is going to be 1,469.4 meters. And if we're being a little bit mindful of significant figures, we can say that that's going to have 3 sig figs, that's going to have 3 sig figs. Our answer should have 3 sig figs. And so this is how we would write that in scientific notation, because there's more than 3 numbers there. We could write it as 1470, but when you put it in scientific notation, it makes the number of significant figures explicitly stated. So that's kind of a nice way to think about these problems when you're working them. Okay, let's look at another example. Here we have a car that is moving at a rate of 61.7 miles per hour. That's 30 meters per second. And they see a deer standing in the road 150 meters ahead. And at that point, the driver slams on the brakes. So we want to determine the minimum acceleration needed to avoid hitting the deer, which we assume does not move. You know, the deer sees the headlights, it's stunned, it's standing in the middle of the road. What acceleration do we need to avoid hitting the deer? And so we can, again, draw our picture. We have our car here, we have our coordinate system, and we know that the initial position is 0 meters, the final position is going to be 150 meters, so that's going to be our delta x. Our x naught we're going to define to be 0. V naught is 30 meters per second, that's what's given in the problem, and we know that V final is 0 because it stops. Now, what are we looking for? We're looking for an acceleration. And so we know that v final is 0. We know that v initial is 30. We're looking for the acceleration, but we don't know the time. So that means that we cannot use this equation. And this equation has the same problem. We don't know the time. Now we might be able to do some kind of crazy algebra and figure things out using both of these equations together, but let's look at the third equation. V final we know is 0, V initial we know the delta x. The only thing we don't know is a. So right away we can see that this equation is going to very quickly give us the path to finding our answer. So here's the equation we're going to use. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Now the final velocity is 0. The initial velocity is 30 meters per second, which is squared. We've got plus 2 times a times the displacement, which is 150 minus 0. That's, of course, our delta x, which is the final position minus the initial position. So what we end up with is that 0 equals 900 meters squared per second squared plus 300 times the acceleration. I move everything over algebraically and I solve for a, and I get that a is equal to minus 3.00 meters per second squared. Now what does that minus sign tell me? The minus sign tells me that the acceleration is opposite the direction of the velocity. We know that we're going to expect that because the velocity is going this way but it's slowing down. That means the acceleration must be in the opposite direction. So that tells us that the answer is negative 3.00 meters per second squared. Let's look at a third example. A helicopter is ascending vertically and it has a constant speed of 5 meters per second. That means it's going upward with 5 meters per second. And at 150 meters above the ground, a nut on the bottom of the helicopter falls off. The question is, how long does it take for the nut to hit the ground? We want to ignore air resistance, assume that little g is 9.81 meters per second squared downward, and there's a hint here. The initial velocity of the nut is not 0. Even though the nut is effectively being dropped, it's being dropped from something that is itself traveling upwards at 5 meters per second. So the initial velocity of the nut is going to be 5 meters per second upward. And so we can draw our picture. We have our helicopter here. It's got a velocity going upward, and we have our coordinate system here, and I've located the origin at the bottom of the helicopter, and we know the initial position in the y direction is going to be 0. The initial velocity is going to be 5 meters per second upward. The acceleration is, of course, g in the negative direction, and the final position is going to be negative 150 meters because the helicopter is 150 meters above the ground, but I put my coordinate system with the helicopter, so it's going to hit the ground, which is 150 meters below the origin. That's why it's negative. So these are what's given, and the question is, how long does it take for the nut to hit the ground? So that's a time. So we're going to be looking to find a time. And in order to do that, we can consider our kinematics equations. Okay, so what we have here is the second kinematics equation. So if we look at the kinematics equations, it becomes pretty clear that this is the one that has everything that we need. And we're looking for the time. We have the final position, which is negative 150 meters. We have the initial position right at the helicopter, that's 0 meters. We have the initial velocity, which is 5 meters per second upward. We have the acceleration, which is basically little g downward, or negative 9.81 meters per second squared. So we have 1/2 at squared. That term is that with little g plugged in. And we move everything over onto the left side. We do so that the squared term is positive. If I moved everything over on the right side, everything would have a minus sign multiplied, and the 4.9 would be minus over here. So we want to move everything over to the side where the squared term is positive, and then we can solve for the time, and we find that the time is 6.1 seconds. How do we solve for the time? Well, we simply plug it into the quadratic formula. That's going to be the easiest way to do that. And just in case you don't remember the quadratic formula, let me tell you, you're going to need it for this stuff. So what we have is, if you have an equation of the form a t squared plus bt plus c equals to 0, that is the form of the equation. And again, you want to move everything over to the side that makes the a term, the one by the coefficient of the squared term, that you want that to be positive. That's the way we've done it up here, so that term is positive. Then the answer is going to be given by the formula t equals to negative b plus or minus b squared minus 4ac, all under the square root, and everything is over 2 times the a term. That is, of course, the quadratic formula, and if you don't remember the quadratic formula, you're going to need to know it. So that's going to be one to memorize. And when you plug this in, what you're going to find is that one of the roots is positive and one of the roots is negative. And what does that mean, a negative time? Well, remember that this formula is a parabola. And so mathematically, it's going to possibly have negative values as well as positive values, because if you were to graph it, it might, look something like that or whatever. And so the time value, this would be the time axis, and so you can have negative values of the time in terms of the equation. But physically, those negative time values don't make any sense. And so we can legitimately throw them out as artifacts of the mathematics. And so that way we keep the positive root, which is just going to be our t equal to 6.1 seconds. So I'm going to encourage you to practice with the quadratic formula if you're a little bit rusty, but you're going to get lots of opportunities to do that on the homework.